So this is your this is your standard formula for exponential growth and decay. You have an initial value, so this could be like what your starting population in a city is. Initial value, and the B here is your growth slash decay factor. So at what rate is the population going up or down, right? And if you take the derivative here with respect to time, dy dt is equal to a times b to the t, and where the derivative of a constant to t is just times ln of b, right? And this right here, a times b to the t, that's just y right here. So dy dt is equal to y times ln of b, but ln of b is just a constant. So we can say dy dt is equal to ky, where k is a constant. When k is greater than 0, that's growth. When k is less than 0, that means decay. So the rate of change of a quantity is proportional to the size of the quantity. Just dy dt equals ky. So we're just going to set up some differential equations. The weight of an animal is increasing at a rate proportional to its weight. So dw dt is equal to kw. Bacteria population is shrinking at a rate proportional to its population size. Let's use P for population. So dP dt equals Kp. It's a P. So we have this differential equation, dy dt equals Ky, what we found earlier. Now let's solve this using what we've learned with separation of variables. So get the y's and dy's by itself. So it's 1 over y dy. Multiply the dt over equals k dt. Do the integral of both sides. So you have ln of y is equal to kt, because k is just a constant, so the integral is just kt plus c. Now you can raise both sides to the e, so on the left we have e to the ln y, which is just y, equals e to the kt plus c. Again, this is rewritten as y equals c e to the kt. If you have a plus c here, it just goes to the front multiplication. In this case here, c is your initial value. So if you read this down here, this is how we get the solution to dy dt equals ky, which is ce to the kt, where c represents the initial value of the model. So find the particular solution for each differential equation. So normally we could, separate the variables and, do all that algebra and calculus. But now that we have this formula here, we can save some time. So y equals, you see when t is 0, y is 5, that's your initial value, c. So it's 5e to the kt, k is just this number right here. So it's 6t. See how quick that was? Question 4. Y is equal to, well, when x is 0, y is 4 here. So this is just 4e to the negative 3. In this case, we're going to use x because this letter here is x, so it's 4e to the negative 3x. So right here, an animal weighs 3 pounds at birth and 4 pounds just 3 months later. 3 pounds at birth, you can think about that as an initial condition. When time is 0, the weight is 3 pounds. The weight of the animal is increasing at a rate proportional to its weight. So if weight is W, dW dt is equal to KW. Set up the differential equation. We just did that. How much will the animal weigh when it's 5 months old? So, hmm, so weight is 3 pounds at birth. So W is equal to 3e to the kt, because 3 is your initial condition here. Now, we can see that at 3 months, the weight is 4 pounds. So when t is 3, w is 4. That's how we can find out what k is. Let's bring this over here. So 4 is equal to 3e to the 3k, because t is 3. And then 4/3 is equal to e to the 3k. If we natural log both sides, we have ln of 4/3 on the left. Again, natural log of e to the 3k, the ln and e cancel out, you're just left with the 3k. So if you divide both sides by 3 here, k is equal to ln of 4/3. Oops, that was messy. ln of 4/3 over 3. On the calculator, that's approximately 0.095. So that's your k value here. So let's plug this back into the original equation. W is equal to 3e to the 0.095. And because this isn't the final answer, let's actually use some more decimals. 0.095 to 894. 894 t. So to find how much the animal will weigh when it's 5 months old, we just plug the 5 into our equation here now. So W of 5 is equal to 3e to the, well, 0.095894, parentheses, instead of t, it's 5. And then on the calculator, you get W of 5 is approximately 4.845. Make sure you do this on the calculator just to make sure you get the same answer right here. If something's off, please ask your teacher. So a growth model will have a positive exponent, so y equals 5e to the positive 2t. A decay model will have a negative in the exponent. Let's try this problem right here. A population y grows according to the equation dy dt is equal to ky, where k is a constant and t is measured in years. If the population doubles every 7 years, what is the value of k? Start off with our general equation, y equals ce to the kt. So they don't give us numbers here, but we know the population doubles every 7 years. So whatever the initial population is, right? Let's say c is y of 0, initial population. E to the, instead of t, it's 7. So k times 7. Our population will be twice our initial. See, twice our initial, because it doubles every 7 years. So now, from here, you can see that y0 cancel out. You're left with 2 equals e to the 7k. If you natural log both sides, ln of 2 is equal to 7k. And divide both sides by 7. So k is equal to ln of 2 divided by 7. And do that on the calculator. K gives you approximately 0.099. You can go ahead and start the practice.